Alright, so we start the next set of exercises. In the first one, we are given these groups. Each one of them is a finite group. For each such, we have to find its order and also the order of each element in the group. So let's start the solution. The first one is the 12. Let us first list the elements in the group. Nine, 10 and 11. So the number of elements in Z12 or Z12, which we also know as the order of the group, is 12. We then have to calculate the order of each element. The identity element always has order 1 and it's the only element in any group having order 1. So the identity element has order, the identity element here is 0. The order of 1 is the smallest positive integer m, such that if we add m number of 1s, the result is divisible by 12. And you can clearly see that for 1, that smallest positive integer is 12. So order of 1 is equal to 12. Order of 2, for 2 we need not go that far. If you add 6 2's, you get 12, and that is divisible by 12, and that is the least number of 2's you have to add so that the sum is divisible by 12. So this is equal to 6. Like that, you can see that the order of 3 is 4, that of 4 is 3. Now for 5, since 5 and 12 are relatively prime, so if you add say k number of 5's, so that you get 5k, and you want this product to be divisible by 12, then relative primality of 5 and 12 would require us to have this, that 12 divides k, and we want the least such k, so k is equal to 12. So that means order of 5 is also 12. Then order of 6 is 2. Order of 7, just like that 5, this is also equal to 12. Then order of 8 is 3, because if you add 2 8's, then you get 16, which is not divisible by 12, but if you add 3 8's, you get 24, which is divisible by 12. Then for 9 it is 4. Adding 2 9's gives us 18, not divisible by 4. 3 9's gives us 27, that is also not divisible by 4. 4 9's give us 36, that is divisible by 4, so the order is 4. Then what about 10? So this will be 6, because among the multiples of 12, the smallest one, that is also a multiple of 10, is 60. You can see the positive multiples of 12 are these. So this one is only divisible by 10 also. So that's why you have to add 6 tens to get the first multiple of 12. So that's why the order is 6. And finally 11 is relatively prime to 12. So here the order must be equal to 12. Next, what about U10? U10 is a multiplicative group where we have positive integers less than 10 and relatively prime to 10. So they are 1, we cannot have any even integer, 3 will be there, 5 won't be there, 7 will be there, and 9 will be there. 1, 3, 7 and 9. So order of U10 is 4, and this is not the notation. The notation from Herstein is more familiar for me, where the order of 1 will be written like this. However, this is also another notation that is being followed in this book, so we are going to stick to this one. Okay, so the order of the identity is 1 always. What about 3? Now, instead of considering multiples of 3, since the operation is multiplication modulo 10, we have to consider powers of 3. So 3 square is 9. Is 9 minus 1 divisible by 10? No. 3 cube is 27. 27 minus 1 is also not divisible by 10. 3 to the power 4 is 81. 81 minus 1 is 80, that is divisible by 10. So that means in this group 3 to the power 4 is actually equal to 1. So this is the smallest positive integer for which this power equals the identity element. So by definition 4 is the order of 3. Like that, one can calculate that the order of 7, here I have calculated them, is also 4, but the order of 9 is 2, because again 9 square is 81, 81 minus 1 is divisible by 10. Okay, so these are the 4 elements and their orders. Next, U12. U12 consists of these integers. 1, so we need integers relatively prime to 12, so we have to avoid even integers and we have to avoid integers that are divisible by 3. So 1, 2, 3, 4 won't be there. So we will have 5, 6 won't be there, 7, 8, 9, 10 won't be there. So 11. Here also, in this group also, just like the previous one, we have 4 elements. So the order of this group U12 is also equal to 4. Okay, now what about the orders of the elements? This one is 1. What about 5? 5 square is 25. 25 minus 1 is 24, which is divisible by 12. So order of 5 is 2. Like that, one can actually see that the orders of 7 and 11 are also equal to 2. Each one of them is 2. Then U20, this will have quite a few elements. So here we have to avoid even integers and also integers that are divisible by 5. That is, we have to avoid multiples of 2 and multiples of 5. So 1, 3, then 5 won't be there, 7, 9, 11, 13, 15 won't be there, 16 of course won't be there, 17, 18 won't be there, 19. So U20 has how many elements? 4 plus 4, 8. And order of 1 is 1, like always. Order of 3. Okay, here I am just going to copy what I have calculated here. Order of 3 is equal to 4. The verification of these things is left to you. Order of 7 is also equal to 4. The fact that this is 4, it just means that 4 is the smallest exponent for which the power 7 to the power 4 is equal to 1 in this group. That means 7 to the power 4 minus 1 is divisible by 20. 4 is the smallest positive integer to make that happen. Then order of 9 is 2. Order of 11 is 2. Order of 13 is, oh, did I miss? No, I did not miss 13. Is again 4. Order of 17 is 4. And finally order of 19 is 2. And finally the last group is the dihedral group D4. We know its elements. These rotations and these reflections about the horizontal axis, about the vertical axis, and about the two diagonals of a square. So order of D4 is equal to 8. And now orders of the elements. R0 is the identity element, so its order is 1. Don't forget that order of any element by definition is either infinite or a positive integer. It is never equal to 0. Okay. We may inadvertently make a mistake of writing the order of the identity equal to 0 quickly. Okay, a silly mistake, but a mistake nonetheless. So try to avoid that. It's tempting to write 0 here, especially when you see 0 here, say R0, Or for example, if you are in a group like Z12 where the identity element is actually 0, you may be tempted to write this, which is wrong. It doesn't make sense. Order is always positive when it is finite. Okay, so this is 1, of course. For R90 this is 4. You compose R90 with itself, you get R180. You do that once more, you get R270, and once more you get R0. So you need 4 R90s to get the identity element. So that's why the order is 4. For R180, however, the order is 2, because if you perform it 2 times in succession, you get back the original configuration. Just like R90, R270 also has order 4. Yes, and the rest of them, they are all reflections. The reflections have order 2 always, because if you reflect once and then again you reflect, you bring the polygon, or I mean in this case the square, back to the original position. So for all of them the order is 2. So this completes the first solution. Then 2. Let Q be the group of rational numbers under addition. Under addition, and Q star be the group of non-zero rational numbers under multiplication. Okay, now what are we supposed to do? In Q, list the elements in this cyclic group. In the cyclic group, according to the notation of this book, this is the cyclic group generated by the element 1 by 2. Just like that, in Q star, list the elements in this. Is there anything? No, nothing else in this exercise. in Q, keep in mind that Q is a group under addition of rational numbers. So we have to add all these 1 by 2s, as many as we can. I mean, as many as we can means we have to consider all possible finite sums and also their negatives. So this, I think it would be better to write in a new line. The identity element, of course, will be there because it's supposed to be a subgroup. Then you have 1 by 2. Then 1 by 2 plus 1 by 2 gives us 1. If you add 3 1 by 2s, you get 3 by 2. If you add 4 1 by 2s, you get 2. If you add 5 1 by 2s, you get 5 by 2, which however I am not writing. You get the pattern. And on the negative side also, similarly you have minus 1 by 2, minus 1, minus 3 by 2, etc. So these are the elements of the cyclic group generated by 1 by 2. In fact, you can see that this set is actually equal to this set, where the general element looks like n divided by 2, where n is an integer. And on the other hand, in Q star, which is a multiplicative group, this group, this cyclic subgroup generated by 1 by 2 consists of all integral powers of 1 by 2. So here also we will have the identity element, which is 1, all the positive integral powers. That means you will have 1 by 2, 1 by 2 whole square, 1 by 2 whole cube, those things you will have. So they will give us 1 by 2, 1 by 4, 1 by 8, etc. And negative integral powers, 1 by 2 to the power minus 1, that gives us 2. 1 by 2 to the power minus 2, that gives us 4, and so on. Okay. So that means in this case, actually this is just the definition of the cyclic subgroup. You have this. Let Q and Q star be as in 2. As in 2 means as in exercise 2. Find the order of each element in Q and in Q star. Okay. in Q we claim that the only element of finite order is the identity whose order is 1. Every other element, every non-zero real number, non-zero rational number has infinite order. Let x be any element in Q such that x is not equal to 0. Okay. Suppose there exists instead of supposing like this, we will directly prove it. Note that for every positive integer n, we have nx not equal to 0. Why? Because n is non-zero being positive and x is already non-zero. So in Q this is a property of rational numbers that if you multiply two non-zero rational numbers, then the result is again a non-zero rational number. So that's what we have written here. So that means for no positive integer n will you get nx equal to 0. So this means that x does not have finite order. Thus does not have finite order. And of course, order of the identity element is 1. That is the only element having finite order. In fact, not just in this group, but in any group. Okay, next, let there we took x, so let us take y here. You can take x also, it's after all a variable. Such that y has finite order. N. Okay, so y is a non-zero element. Non-zero element means elements here are non-zero. Y is a non-zero rational number. So it has a finite order n. Say, then we try to determine what y can be. Then y to the power n is equal to 1, which implies absolute value of y to the power n is also equal to 1. To see why this is true, what you do, you take absolute value on both sides, but absolute value of y to the power n is equal to absolute value of y whole to the power n, so that this becomes equal to 1. Okay. Now if n is equal to 1, then absolute value of y is equal to 1. If n is greater than 1, I mean these are the only two possibilities. Since n is a positive integer, so n can either be 1 or greater than 1. Then recall one identity from elementary algebra. This product is equal to absolute value to the power n minus 1, which is equal to 0. Okay, so that means this is a rational number, this one, that factor is also clearly a rational number, since y is a rational number. But note that because y is non-zero, absolute value of y is a positive rational number. So that means this factor, this sum cannot be equal to 0. And additionally you have plus 1 here also. Since y is not equal to 0, we have this not equal to 0. So from the above arguments or calculations, from the above calculation, we conclude that their product is 0. This is non-zero, that means this must be equal to 0. That is, absolute value of y is equal to 1. So you see that in any case, whether n is 1 or greater than 1, absolute value of y must always be equal to 1. So in any case we have one. This implies y is either minus 1 or plus 1. Okay, that is, the only elements of finite order in Q star are minus 1 and 1, and order of minus 1, keep in mind in Q star the binary operation is multiplication. So what is the smallest exponent for which minus 1 to the power that exponent will give us 1? 2. So here the order is 2 and the order of 1 of course is 1 because 1 is the identity element. So this completes the solution to the third one. Okay, Does that formula make sense for the condition that we have chosen under which we are writing this? N is greater than 1, so that means the smallest value of n can be 2. If n is 2, then this becomes absolute value of y. So that means in the smallest possible case, this factor is actually absolute value of y plus 1. Yes, fine. So next exercise 4. Prove that in any group an element and its inverse have the same order. Prove that in any group an element and its inverse have the same order. Let A be an element in a group. Okay. First, assume that A has infinite order. Let's deal with that case first. Now we want to prove that A inverse also has infinite order. For that we will prove that by contradiction, by supposing that no, A inverse has finite order, and then we will arrive at a contradiction. Suppose A inverse has finite order, then let us call it by some name n, which is equal to the order of A inverse is a positive integer. Now, n being the order of this means what? That if we take the nth power of A inverse, then we are going to get the identity. But by the rules of exponent, the inverse of this element also is equal to identity, because the inverse of the identity is identity, which implies now this is where we are using the rules of exponent. Or if you take the product of these integers, you get a to the power n equal to identity. Now note this final equation. This says that A has finite order, because since n is a positive integer, so this corresponding power has become equal to identity. So A will have finite order, and the order of A will be less than or equal to n. I mean, n is one such integer, order is also one such integer, but the smallest one. This implies A has finite order. a contradiction. So our supposition is wrong. That is, A inverse must also have infinite order. Next we handle the finite order case. Next, assume that A has finite order m, say. So that means m is some positive integer. Okay, then A inverse to the power m is equal to, by the rule of exponent, this is equal to A to the power m inverse, but m is the order of A, so A to the power m by definition is the identity. Identity inverse is equal to identity. So we have proved that this mth power of A inverse, this power is equal to identity. This equation just proves the fact that the order of A inverse is finite. But now we have to additionally prove that the order is not just finite but actually equal to m. So for that, suppose there exists a positive integer k less than m such that A inverse to the power k is equal to identity. We have supposed that there is one such k that is less than m and still the kth power of A inverse equals identity. Now this will create a problem and that's what we want. Then A to the power k inverse is equal to identity which implies A to the power k is equal to identity. To obtain this from this one, you can argue in two different ways. One is that since A to the power k is an element whose inverse is identity, so A to the power k must itself be equal to identity, because identity is the only element whose inverse is also equal to identity. No non-identity element will have its inverse equal to identity. The other way is that you take inverses on both sides. On the left side, you use the fact that the inverse of an element in a group is the element itself. And on the right side, you use the fact that the inverse of the identity is identity. So that's how you get this one. But this contradicts the minimality of m. Since m is the order of a, so m is the smallest positive integer for which a to the power m equals identity. But here we have got an even smaller positive integer such that the corresponding power equals identity. So if this is true, then m cannot be actually be the order. So this is a contradiction. So our last supposition is wrong. That is, there is no such k. And that means no integral power of a inverse smaller than m will give us identity. I mean this one. If you have here a positive integer that is smaller than m, then a inverse to the power that integer can never be equal to identity. So that just tells us that m is actually the order of a inverse. Hence, the order of a inverse is also equal to m. So this proves that a and a inverse have the same order. Next, five. Without actually computing the orders, explain why the two elements in each of the following pairs of elements. Explain each of the two elements or not each of the two elements. Why? The two elements in each of the following pairs of elements have the same order. Two 28, 822. Do the same for the following pairs of elements from U15. 2, 8, 7, 13. Okay, and here clearly we have to use the result of the previous exercise, because if you notice in Z30 these two elements are actually inverses of each other, and so are these elements 8 and 22, because if you add these two you get 30, and if you add these two then also you get 30, so that means they are inverses of each other. Since in Z30 or C30 2 inverse is equal to 28 and 8 inverse is equal to 22, so orders of 2 and 28 are equal and orders of 8 and 22 are equal, and for to conclude these equalities we did not have to actually find the orders, and you can also write if you want that we are using the result from the previous exercise. In U15 2 inverse is 8. Why? Because 8 times 2 is 16. 16 minus 16 congruent to 15 is 1. Like that, 7 times 13 is what? 91. 91 is congruent to 1 modulo 15, because 90 is divisible by 15. 15 times 6 is 90. This and 7 inverse is equal to 13. So the orders of 2 and 8 in this group are equal, and also the orders of 7 and 13 in the same group are equal. Then exercise 6. In the group C12, find these orders. Order of A, order of B, and order of A plus B for each case. And the cases are these. In case A, we have A equal to 6 and B equal to 2. In case B, we have A equal to 3, B equal to 8. And finally in case C, we have A equal to 5 and B equal to 4. Something else is also there. Do you see any relationship between these? between three quantities or among three quantities? So we just have to find the orders, and the group is Z12. We have already seen that in this group, order of 6 is 2, keeping in mind that this is an additive group. The operation is addition. Order of 2 is 6, and order of 6 plus 2, 6 plus 2 is 8, and order of 8 is 3. In part B, order of 3 is 4, order of 8 is 3, and order of 3 plus 8 is 11, order of 11 is 12. We already calculated these orders in the first solution. C. 5 is relatively prime to 12, so the order is 12. Order of B is 4. Order of B is order of 4, that is 3, and what is A plus B? A plus B is 9. 9 means 4. Okay, now what relationship among these quantities can be excuse me, guess. One thing that I can see is this. I don't know whether I am correct or not, but in general I am correct or not, but at least in this example that seems to be the case. The thing is that if you take the LCM of these two orders, okay, and you divide by GCD, then you get the order of the sun. Is it really the case? Let us see. LCM of 2 and 6 is 6, and GCD of 2 and 6 is 2. 6 divided by 2 is 3. What about here? LCM of 4 and 3 is 12. Okay. GCD of 4 and 3 is 1, because 4 and 3 are relatively prime. Yes. And for the third one, what is the LCM? Least common multiple is 12. And GCD, greatest common divisor, is 3. So 12 by 3 is 4. Yes, it's matching. So that is our guess. It's only a guess at this point, but in general it may be true, may not be true. I should know that, but I have forgotten actually. 7. If A, B and C are group elements, and order of A is 6 and order of B is 7, then express this element A to the power 4, C to the power minus 2, B to the power 4 whole inverse without using negative exponents. Okay. Since A has order 6 and B has order 7, we have some more ink. A to the power 6 is identity and B to the power 7 is identity. I hope these are visible. From these, we have A square is equal to A to the power minus 4 and B cube is equal to B to the power minus 4. Now this is our element. So this will be equal to, by elementary group properties, inverse of this times inverse of this times inverse of this. Now use the rule of exponent that gives us b to the power minus 4 c square a to the power minus 4. Now use these relations. B to the power minus 4 is b cube, c square, a to the power minus 4 is a square. So the given element has been expressed in this form where we don't see any negative exponent. In fact, we don't even have a zero exponent. Then 8. What can you say about a subgroup of D3 a subgroup of D3 that contains this rotation R through an angle 240 degrees and a reflection F. What can you say about a subgroup of D3 that contains two reflections? Subgroups of the dihedral group D3. Okay. Let H be a subgroup of D3 such that we cannot can we take let us take some other symbol, because these H and F and R, they have already been used for elements. So let us take A such that R240 belongs to A and some reflection also belongs to A. Now, since A is a subgroup, the following elements are all in A. R240 square and R240 cube, which is actually equal to R naught. R240 square is not equal to R naught. Okay, R240 square is a rotation through an angle 480 degrees. R240 cube is a rotation through an angle 720 degrees, which is divisible by 360 degrees, and hence it's a complete revolution. So that brings us one complete revolution or several complete revolutions. How many I can't, it does not matter actually. The thing is that after you perform this operation R240 cube, then all the things will come back to their initial position. So that's why it is the same as the identity map. And note that R240 square and R240 cube, these are all distinct elements in D3 because of the cancellation law. If you say assume R240 equal to R240 square, then you can cancel R240 from both sides using one of the cancellation laws, and that would give you R240 equal to R naught, which clearly is not true because R240 is not the identity map. Like that, these two also cannot be equal, because if they are equal, then again cancelling R240 square from both sides, you get the same contradiction that R240 is equal to the identity map. and if you assume this is equal to this, then you are actually assuming R240 equal to R0. Again that same contradiction. So these are three distinct elements in the subgroup A. So we can mention that. Note that R0, R240 and R240 square are three distinct elements in A, but it's given that A has F also. Now, since F belongs to A, we have FR240 and FR240 square also belonging to A. And just like we proved that these three elements are distinct, we can also prove that these three elements obtained from this by multiplying them by F are also distinct using the cancellation laws. What more is true, these elements are also distinct from these elements because these are rotations. However, each one of these, this one is a reflection, it's given to be a reflection. This one is a product of a rotation and a reflection. So it has to be a reflection because it ultimately changes the orientation. Just like that, this one also is a reflection. So we have actually got how many elements? 1, 2, 3, 4, 5, 6 elements in the subgroup A. But we know that D3 itself has 6 elements, so that means A has to be equal to D3. Now, one can show that if FR240 and FR240 square are all distinct, in fact, let me just mention it. Use the cancellation laws to show this. Moreover, these two sets are actually disjoint. The first set consists of reflections, whereas bad penmanship. Thus, order of A is at least 6 because we have got 6 elements in A. However, A is a subset of D3 and order of D3 is equal to 6. Hence, A must be equal to D3. Okay. Next, again one subgroup is there which contains 2 reflections. Let B be a subgroup of D3 that contains two distinct reflections, say F1 and F2. Then their product should also be in B because B is a subgroup, and we know that the product of 2 reflections is actually a rotation because we get the original orientation back if we reflect twice. The axis of reflection does not matter, the orientation comes back. But which rotation, that is the note that F1, F2, let's also mention that this belongs to B, and F1, F2 is a rotation. Moreover, F1, F2 is actually not equal to the identity. This follows from exercise 41 of the previous exercise set. So that means now we have a reflection in our subgroup, a rotation in our subgroup that is not the trivial rotation. So we already know that there are only 2 non-trivial rotations, either R240 or R240 square. This one will be one of them. Okay, if it is R240, then we have come back to the previous situation, because now in our subgroup we have R240 and one reflection, which you can take any one from these 2, and you can argue exactly similarly to conclude that B is also equal to D3. And if this rotation happens to be R240 square, then also you can show that R240 is still there in B, because if you take powers of R240 square, R240 will come at some point, and that is because R240 cube is equal to identity. And you come back to the same position. So we are just simply going to write like this. Thus one can argue like above to show that B is equal to D3. That means in the dihedral group D3, if a subgroup has R240 and at the same time a reflection, then the subgroup must be equal to D3. And also if the subgroup has two distinct reflections, then also the subgroup must be equal to D3. So that's what we can say about such subgroups. Then there is exercise 9 also is of that nature, but instead of D3 we have D4, and then several such other exercises are there. So let's just end the video here itself. We will do more in the next video. In the meantime, if you have any doubt or if you can find any mistakes in these things that we have been doing, then please feel free to let me know in the comment section. And if you are new here, please subscribe to my channel. These things have to be said because after all it's YouTube. So with that I sign off. This is me, Lucifer, from a mathematical room. Have a nice night.